Hello, in this video we'll be going through another kinematics question. We've got a particle P moving along the x-axis, so we're only in one dimension, makes things easier. Time t seconds for positive t, the displacement x is given by this function here. So I'm going to write that out a bit bigger, make sure everyone can see it. X, the displacement, is a half of t squared multiplied by t squared minus 2t plus 1. Right, so this is variable acceleration, because if we had constant acceleration then our displacement function would be a quadratic, but this is a quartic, so it must be variable acceleration. For part A, we need to find the times when P is instantaneously at rest, so i.e. when the velocity is equal to 0. Right, so the velocity is the rate of change of the displacement, which is dx dt. So we need to differentiate this function and then find, set v equal to 0, i.e. we're finding the turning points from a graphical point of view, just thinking, straight calculus, we want to find the turning points of this displacement function, because every turning point is a point of instantaneous rest. Right, so rather than use the product rule, because there's only 3 terms, if we multiply this out, I'm going to differentiate each term individually. So we've got a half t to the 4, which will go to 2t cubed when we differentiate. We've got then a minus t cubed, which will go to minus 3t squared, and then just that thing on its own, which is going to be a plus t when we differentiate. So I think that's easier than having to deal with a product rule in this particular case. And then we can say when v equals 0, we're going to have, well, we need to factorize all of this, don't we? We're going to have 0 is equal to t, that's one factor, and 2t squared minus 3t plus 1, yeah, that is going to factorize into 2t minus 1 and t minus 1. So it's quite an easy factorization to do on that one. So that means that t will be equal to 0 or a half or 1. So we've got our times when the particle was instantaneously at rest. This does mean we've got the information now to sketch out this function. This part of the question could have just been a pure maths question of, well, let's draw this. So that might be something that we're going to want to do in a moment anyway. What is part B? Find the total distance travelled by P in the time interval 0 to 2 seconds. Right, so yes, actually it is going to be useful to draw that out, because it's asked us for total distance, not the change in displacement. And remember, whenever we're looking at total distance travelled, we have to beware velocity change in sign, because that doesn't get picked up if we just do an integral over the whole time period, if there's a change in sign in the velocity. So we want to do a sketch of this displacement graph in order to see if the gradient has changed, so we know what to do with our integral. So let's get the actual coordinates of these turning points, and we've got the times when things are turning, so let's get the displacements of when there's instantaneous rest. So when t is 0, then we're going to have x is equal to 0, because we've got this t squared on the outside. When t is a half, we've got a half times a quarter, that gives us an eighth, and then inside the bracket we've got a quarter minus 1 plus 1, so an eighth times a quarter is 1 over 32. And when t is 1, we're going to have a half times 1 minus 2 plus 1. All right, so that's 0 as well. So now we've got the coordinates of the turning points. We know it's a positive quartic with 3 turning points, so it's going to be some variation on a W shape. And we know that because it's positive, we've got 2 minimums and a maximum. So let's try drawing this out. Oh, we can see that we're not going to get any negative x values from what we've already got, because these are our two minimums, the ones on the outside, when t is 0 and 1. So we've got a one minimum point at 0, 0, and we've got another minimum point at 1, 0. So they're our two minimums. And we've got a maximum at a half 32. So let's draw in the shape, and then I'll mark on where the half is afterwards. So our quartic is going to be looking something like this, and this maximum here is going to be at 1 over 32. So we can see with this that we have got a change in sign in the velocity. If we're going from 0 up to 2 seconds for our integral, then here we've got positive velocity, here we've got negative velocity, because this is our displacement time graph. And then here we've got positive velocity again. So we need to divide this up into 3 regions to make sure we're getting total distance travelled. So for part B, so how far have we travelled in 0 to a half? Well, we've gone from 0 to 1 over 32. So for 0 to a half of a second, we've travelled 1 over 32 meters. And then for a half to 1 seconds, we've also travelled 1 over 32 meters, because we've gone back to 0 displacement. And if we're just integrated from 0 to 1, that would come out as nothing, because we've ended up back where we are, back where we started. You know, the displacement hasn't changed. When we just look at 0 seconds and 1 second, you know, we're back at the starting point. So we would lose that travelling distance of 2 lots of 1 over 32. Then when we go from 1 up to 2 seconds, well, we know if we're starting at 1 second, we're at 0 displacement. So at 2 seconds, where have we got to? If we put 2 into, time t is equal to 2 into our x function here, then we get a half of 4, which is 2, times 4 minus 4 plus 1. So 2 times 1 is 2. So we've moved 2 meters. So in total, the distance travelled is 2 1/16 of a meter. That's our distance travelled. If we'd just done what's the change in displacement, it would come out as 2 meters, because that's where we ended up after 2 seconds. So yeah, always got to be careful when it's looking at total distance. And then for C, show that P will never move along the negative x-axis. Well, actually, our graph does that. Our graph is showing us here. So we can say, yeah, from sketch of x versus t, we can see that, yeah, x is always greater than or equal to 0. And that's for all time, not just for positive time. So that must show up then in our actual x function. We must be able to write this out. Ah, yes, see, I hadn't spotted this at the start. You might have spotted this right at the beginning. I've only just seen it now. We can rewrite our x is equal to a half. So we've got a half t squared, but of course that bracket is a perfect square. That is t minus 1 squared. So everything in here is positive. We got a half times something squared times something squared. Which is a perfect square. Perfect square. So therefore it must be greater than or equal to 0. Yeah, so sometimes you only spot these things at the end when you've found out the answer from other means. But yeah, if you'd spotted that right at the beginning, it would have been obvious that that was going to be the case. So yeah, again, that's the thing that they try and get people with, this total distance. It comes up in quite a few of these questions, because it really does test your understanding of displacement versus distance, and how we take that into account by looking at the velocity. So yeah, that's a tough question.